Let's see if I got that started. Yep. Okay. Full disclosure, I know that we're a little behind on getting some of the homeworks graded and whatnot. We're working on it. Right now, the solutions to all of the outstanding homeworks are posted. My goal is to try and get that backlog cleared up as soon as possible. So I am aware of that. We're working on it. So homework 3.6 is due today, and then homework 3.7 is assigned today. And today will be our last lecture on rigid body systems. And so the whole concept of rigid body systems was really about defining a moment, like what is a moment, what are the various, sort of classic examples of moments. So moments in two dimensions, moments about an axis, force couples, etc. And we really ended on this concept of an equivalent system. I have system A and system B, and if they have the same sum of forces and the same sum of moments, we say that they're equivalent. What we will then do is the next natural extension to this concept, which is rigid body equilibrium. I have a rigid body subjected to a series of forces. What are the forces, the external reaction forces required to keep the structure in equilibrium? And so that's going to be sort of the statics, if you will. We'll have 4 lectures on that, which are mostly just a lot of example problems in 2D and 3D respectively. In terms of our schedule, we have our exam review on Monday, October 18th, and we have our second celebration on Wednesday, October 20th. Okay. After that, we'll basically be done with the formal introduction of the 2 main concepts in this course, which are forces and moments. The rest of the semester will be about using those concepts to attack classical problems in engineering mechanics, like the computation of the location of a centroid, learning how to analyze a truss system, learning how to construct shear and moment diagrams, etc. These are classical problems in engineering mechanics that we will spend the rest of the semester trying to digest. Okay, any questions? All right, so today's lecture slides are, just like last time, are very short. The idea is that ultimately what we're after is this right here. We're after taking a system of forces and resolving them into a much more simple system that meets both sum of forces equivalency and sum of moments equivalency. Last time we focused on 2-dimensional problems. Today we will focus on 3-dimensional problems. And I decided as I was walking over here today that I'm calling a little bit of an audible on my notes. We have 2 examples today that we're doing in 3 dimensions, and I actually want to do this one first. Okay? I want to do this one first for 2 reasons. One, I think the math is simpler. We can do this problem from start to finish. It is much more in line with your homework assignment. And really, this problem is just, I would say, additional practice. I gave you a lot of the vectors that sort of comprise the grunt work of this problem. So I figure we'll look at this one later. I really want to look at this problem, and I want to show you the equivalent system component of this problem today, and I want to make a point about this problem at the end, because this problem has a hidden introduction to a concept we're going to discuss after the second exam. Okay, this is also a problem, maybe it's a little bit more near and dear to my heart as a civil engineer. So we have a square foundation, and the square foundation is this, we'll say, concrete mat, and it is supporting the loads from 4 columns as shown. So let's say this foundation is holding up some columns in a building, and so the columns in the building are pushing down with the series of loads. We have 40 kips, 12 kips, 8 kips, and 10 kips. We want to determine the magnitude and the location of the resultant on this mat. So the idea is that if I were to take these loads and represent them with just a single load, where do I put it on this mat such that it meets both force and moment equivalency? Okay. One of the reasons I like this problem is because the forces you can write the IJK vector description of the forces and really the position vectors by just looking at it. This problem, there's a lot more going on. There's a lot more geometry. It doesn't make the problem conceptually harder. It's actually kind of the same concept. It's just the actual grunt work of writing the vectors and describing the vectors just takes a lot more work. And I don't see much value in us just doing the same thing over and over again and not advancing forward conceptually. So I want to look at this problem first. So let me pull the notebook up. This is last class. And we're going to do this problem first. Okay. So I have a foundation mat supporting these four loads. Let's look at the loads first. So before we start chugging the math away, let's look at our process and make sure that our process makes sense. So we describe each of the forces in IJ notation or IJK notation. We describe the position vectors in IJK notation. And then we do R cross F, and then we have sum of forces and sum of moments, and then we go from there. Let's look at these forces. Can you tell me along which axis are all of these forces acting? The y-axis. They're all acting up or down? Down. So the vector description is actually very easy. For instance, if I'm looking at this load applied at C, I have 12 kips going down. So I propose that the force at C is negative 12J, you know? Same thing, negative 8J, negative 20J, negative 40J. The force description is very easy. So that's one of the reasons I kind of wanted to do this problem first. All right, so give me 1 second. I was lazy. I copied the problem again. So force vector description. And maybe what I'll do is I'll say in kips. Remember, 1 kip is 1,000 pounds. Let me make this a little bigger. All right. So what we'll do is we'll say, let's come up with a numbering scheme. Let's say this is 1, this is 2, this is 3, this is 4. Just so we're all referencing the same thing, okay? So F1 is negative 40J. F2 is negative 12J. F3 is negative 8J. And F4 is negative 20J. That should be pretty easy, right? I'm not doing that too fast, am I? Okay. Now, for our position vectors, we need to pick a point about which moments should be taken. Ultimately, the purpose of this problem is to come up with a single load placed on this mat that has force and moment equivalency. So it actually really doesn't matter where we sum moments from. Now, that being said, that doesn't mean I have to make the problem difficult for me as the analyst. So if I look at this coordinate system, I think what might be easiest is to take moments here. So we'll say take moments about O, okay, the origin. So the idea is if I was describing some of these vectors, I might say this is, let's say, R2. This might be R3. And this might be R4. Make sense? Remember, a position vector is defined that starts at the point about which moments are being taken, in this case point O. So it goes from point O to the line of action of the force in question. So all I'm doing is I'm saying, like for instance, R2 goes from the point in question to the force, the point in question to the force, the point in question to the force. Now I've got R2, R3, and R4 written. Why don't I have R1? What is R1? There you go, exactly. It is 0. I might write it like this. It's technically the 0 vector, but you're exactly right. If it starts at O and ends at O, there is no position vector. So I guess the more obvious question is, does the 40 kip load generate moment at point O? No, it doesn't, because it goes right through point O, right? Remember, moments are only generated when they cause a tendency to rotate. That 40 kip load does not want to cause point O to rotate. The others do, okay? So R2, R3, R4, now that's a different story. So R2, let's see if we can do R2. Can somebody tell me what is the description of R2 going to be? Remember, this is the x-axis, this is the y-axis, this is the z-axis. Do any of these vectors have a y-axis component? No. So what about R2? What's the description for that vector? 10i. Exactly right. All right. What about R3? 10i plus 5k. That's exactly right. (10i plus 5k). And then R4 is going to be 4i plus 10k. Did I do that right? Yeah. There you go. Not too bad, right? So far, so good? See, I like doing this problem first. I think I'm going to maybe switch this up in the future. I like this problem first because the vector description is very easy. We describe the F vectors, describe the R vectors, then it's time to start rocking and rolling. So once we have this, we can now sum forces and moments. So the idea is, okay, let's take my forces. I've got force 1, force 2, force 3, force 4. First off, write my R vector. That's in feet. So I'm going to repopulate that table. So we have a 0 vector. We have 10i. We have, oh, that's wrong. That needs to go like that. We have 10i plus 5k. And we have 4i plus 10k. And then the F vectors, which are in kips. So this is negative 40i, negative 12j, negative 8j, negative 20k, or negative 20j. All right? And now what we need to do is we need to start summing. The first thing we need to do is we need to sum the force vectors. So that's really easy for this problem, right? All the forces are acting downward. So all we have to do is 40, 12, 8, and 20 gives you what? 80. Or negative 80, but yeah, the magnitude is right, yeah. So negative 80j. So that's my resultant vector, okay? Now what we need is R cross F. Now remember, that's in foot kips, so now one of the things I haven't really heavily emphasized yet in here, but I don't think is the worst idea in the world, is when you start doing problems like this, you're just going to be doing cross products over and over and over again. Your scientific calculators as well as your graphing calculators have native functions enabled inside them to do cross products, so I would sort of learn that. When we first introduced the cross product on that pre-recorded lecture, I showed you how to do that on the Casio. What I might do is compile a similar list of playlists for, like TI graphing calculators and HP and so on and so forth. If you saw on Teams, I showed you how to do that for simultaneous equations. I might do that here because you're just going to be doing cross products over and over and over again, and I don't want you to have a problem on a homework or exam because of this. Like, once you know how to do it, let the calculator do the work for you. All right, the first one. Now, I don't need any math for this one. I don't need a calculator for this one. For force 1, if I take R cross F, what do I get? 0. That's a 0 vector. Now, what about this second force? 10I crossed with negative 12J. So this second one here, I'll put something down here so that we can kind of follow. What I'm doing is this. So 10, 0, 0, 0, negative 12, 0. That's what I'm doing for this row right here, right? Now, like I said, if you want, you can do this off to the side or maybe get your calculator to do the heavy lifting. So I, 0, 0, negative 12, 0, minus J. 10, 0, 0, 0, plus K, 10, 0, negative 12, sorry, I did that backwards, 0, 0, negative 12. Do y'all see what I did? So if you look at this, that's going to be 0, that's going to be 0, and what's going to be left is minus 120K. Does that make sense? Everybody okay with that? All right. I want to test you and make sure you're following along with me. Can somebody give me M3? What is this one going to be? I'll give you a minute. So you're going to take this vector, cross it with that. And I don't care how you do it. You can do it in your calculator. Yes? That's a great question. So the question was, can you do the RxFy minus RYFX? I'm going to say no because this is a 3D problem. Now, let me say this. There are some times that the moments truly are in 2 dimensions, right? So, oh goodness. For example, this one right here is sort of a 2-dimensional problem, right? Because the R vector is I comma j, and this is I comma j. This is sort of a 2D problem. But this one isn't, right? Because the R vector has I components and K components, and then the force vector has J components. So because this problem truly is in the 3rd dimension, you kind of need to chug out the determinant. That's a great question. So yeah, on row 2, yes. Row 3 and row 4, no, I don't think that's going to work. That's a great question. Any other questions? All right, does anybody have an answer for this one right here? Whether you did it off to the side or let your calculator do the work, it doesn't matter. Anybody have an answer? Does everybody know what I'm asking? Like that's the big thing. Like I know that you might have to grunt this out a little bit. That's okay. I just want to make sure you understand what we're doing. Anybody have an answer? Don't be shy. I'm going to wait. Just so we're clear, what we're doing is this. So we're doing we're taking that vector and that vector. And we're crossing that. That's what we're doing. Anybody have an answer? Yes. Okay, 40I minus, what'd you say? 180K. Okay, I got the 40, but I didn't get the 180. I got something different. Yes?
I just got 80K.
That's what I got. I got 80K. Did anybody else get that? Okay, all right, there we go. So 40I minus 80K. That's what I got. And then I'll go ahead and do the last one. So when you do this one cross with that one, you get 200I minus 80K. All right. And I'm going to take this part right here and sort of just like move it down. All right. So my moment vector is just summing these up. And so all you have to do is sum up the I terms, sum up the J terms, sum up the K terms. So if I sum up the I terms, I have 0, 0, 40, and 200. So I get 240. And then negative 120 and negative 80 is negative 200. Negative 200 minus 80 is negative 280. Negative 280K. So to draw the analogy from what we did last time, we now have a system that has R is negative 80J and M is 240I minus 280K. This is system 2. And that system 2, if this is system 1. So system 1 has a bunch of individual loads. I have now simplified that into two vectors, a force and a moment. Ooh, excuse me. Now we're not done yet, but that's sort of the idea on the problem so far. Any questions? Okay, so let's talk about what the problem is about, okay? The problem is about the following, okay? Let me move this up here. All right. All right, let's determine the location of the resultant force. So here's what's going on. All right, and please forgive my horrendous three-dimensional art skills. The idea is that the original problem involved a foundation slab that looked like this, okay? And in terms of our axes, this was the y-axis, this was the x-axis, and this was the z-axis. All right, I'll draw lines through my z's, that way I know it's not a 2. So, okay. Now, the idea is that the original slab had 4 loads on it. What I want to do is replace that with just a single load, okay? So I propose that single load would be, I don't know, maybe right here. Now, in order for that to have static equivalency, that load must have a magnitude of 80 kips, okay? But the idea is to figure out where to place it, okay? Well, I have to place it in that magic spot so that it generates the same amount of moment, okay? So what I need is a description. Oh, hold on, I can do better than that. What I need is a description of this position vector, R. Remember that this point right here, that's point O. That's the point about which we took moments at the beginning of the problem. Now, the way that I'm going to do this is as follows. Let me move that label here. I'm just going to remove that. All right. Again, forgive my horrendous three-dimensional art. Okay. I propose that here's the vector, R. Let's look at the position vector. All right. Now, I don't know what these distances are, so let's call this dimension here, I don't know, let's call it this dimension Rx, okay, because it's along the x-axis. And let's call this dimension right here Rz, because it's along the z-axis, right? So I propose that my position vector would be Rx times I plus 0j plus rzk. Is everybody okay with that? And then my force vector, in this case, is going to be the resultant, which was just 80 kips going down. So 0I minus 80j plus 0k. And when I do R cross F better equal 240I 0j minus 280k. And where am I getting that? That's this right here, right? So I propose that this is my position vector, this is my force vector, and when I cross those, I better get this. So the idea is, what does this value and this value need to be such that that is true? Such that that system is equivalent. Does that make sense? Okay, so let's see what we get. All right, so let me scroll down. Now, I know it looks kind of nasty because you're like, okay, wait a minute, Dr. Mike, you got two variables here. What's going on? Trust me, this is actually going to be a lot easier than you think. So let's take R cross F. So Rx, 0, Rz, 0, minus 80, 0. So we take I, cross out the rows and columns related to I, and we're left with this box right here. So 0 minus 80 Rz 0 minus J. Strike out the rows and columns associated with J. Strike out that and that. I'm left with this column and this column. Plus K. Strike out the rows and columns associated with the K vector, and I'm left with this box right here. Rx 0, 0, minus 80. Does that make sense? So for the I term, what are we going to get? We're going to get this times this minus this times this. So this is something where you really got to make sure that you're watching your signs. 0 minus negative 80 Rz. For the J component, that's just 0, right? Because this times this is 0, minus this times this is also 0. So that's 0. Plus K. And so what do we got? Negative 80 Rx minus 0. So if I simplify this math a little bit, I get, what do I got? I got 80 RZI plus 0j minus 80 RZ K, right? Oh, you're right, thank you. And as we said, this has to equal 240I, because this was our moment vector, plus 0j minus 280k. Looks like that's going to be pretty simple, right? Because if 80RZ equals 240, RZ is 3, 280 equals 80 RX. RX is, what is that, negative 3.5? And these are positions, these are in feet. So the idea is here's your slab. Here's your resultant. And this dimension here is 3 feet. And this dimension is 3.5 feet. Huh? Well, RX is along the x-axis. That's the dimension. Yeah, I get what you're saying. Yeah.
Is this basically just taking a weighted average of position?
That is a great question. I want to talk about that a little bit more here in a bit, because you're not wrong.
That feels like a lot of work to take a weighted average.
It's a little bit more than that. Okay, it's a little bit more than that. Let me explain why. Bear with me. I'm gonna get there. So, first off, that's the answer. So before we address your question, because you are making a very good point, but before we address your question, does everybody understand what we've done so far? Now, what you're asking is, so the question he asked was, isn't this spot just sort of a weighted average of the four applied loads? The short answer to that is yes, it actually is. Okay? Here's the longer answer. That doesn't quite work out when your loads aren't all vertical. And when they're not all vertical, you kind of have to go through this process. But there is an equivalent statics-based process that we can do that is a lot simpler. Okay? And I propose that I have a better name for this point instead of calling it the weighted average. I propose, and to answer your question, I wouldn't do this problem this way, okay? But the idea is that, I'll explain why I did it this way here in a bit. But instead of calling that location the weighted average, I propose that another name for that location is the centroid of that load group. I told you a while back that we're going to be computing locations of centroids, and that later on, if we compute the location of the centroid of those 4 loads, it'll be right there, okay? Does that make sense? Now, why did I show you how to do it this way? Okay? Well, there's 2 reasons why. First off, does everybody have this? Okay. The first reason, I closed my notebook. I didn't mean to close my notebook. The first reason why is because of this problem right here. That old weighted average approach, it's going to be a little tough on this one, right? That's a great point. And when we talk about centroids, That's kind of where we're going with this. Okay, that's kind of where we're going with this. And the fact that you're making that determination is kind of brilliant, because that's kind of what a centroid is. In fact, what I would argue is that the principles of statics are obeying those concepts in general, right? That the idea is that these definitions of R cross F, etc., are obeying that, okay? Now, what you're talking about, we're going to get there, but we're going to do that a little bit more formally, because I'm not just interested in centroidal applications of, what's the centroid of a load group. I want to know what the centroid is of an area, of a volume, of a group of lines. And so we will tackle that, trust me.
I was going to say, like, for volume, that would just be like center mass.
Basically, that's what this is. That's one of the applications of forces and moments. Okay. I propose to you that the center of mass of an object is the point about which you can idealize the entire volume or component of that object as a single vector, and it respects force and moment equivalency. That's the whole point, okay? That's a great question. Does that make sense? This is a great question. I love this. The fact that you made that observation, I'm kind of glad somebody did, okay? Another thing that's worth mentioning is, how do you think that a computer does this? This is how a computer does it, okay? I guarantee you, this is how computers do this in 3 dimensions. Speaking of, I do want to talk a little bit about this problem. So this problem is the one that I skipped. I said I'm going to call an audible. Let's do that one first and then this one. Why? Well, because I promise you that the R cross F component, at least from a computer standpoint, from a computational standpoint, is far more computationally efficient in terms of chugging this out. I just want to show you that the idea is that for a problem like this, I know this problem looks nasty. The idea is that it really isn't, okay? That's kind of the point I want to make. I have a bracket here, and the bracket has 3 forces on it, and these forces look pretty rough, okay? Like, for instance, I've got this 1,000 Newton force acting over here sort of on this XZ plane, if you will, at a 45-degree angle. And if you look at the force, ultimately I've got that described here. The idea is that even though the problem looks nastier, the process is exactly the same. What do? You describe each of the vectors, each of the position vectors. In this case, I'm describing all the position vectors from the point A. What happened there? Somebody messaged me.
No, that was mine from like an hour ago.
Oh. You interrupted class in a different way. No, I'm just kidding. Okay. So you sent the message, but it just went through?
Yeah, I sent that like 20 minutes before class started.
Oh.
So, right at an hour ago.
You made the YouTube video.
Thank you.
you're
and making YouTube all in one day.
All right. I lost track of what I was talking about here. Which, by the way, I will say, I'm not repeating it, but somebody took the attendance joke that I mentioned in structural analysis. I had a really humorous person sign the attendance last time. I'm just going to leave it at that. That was, yeah, I'm not repeating that. So they know who they are. Okay, so the idea behind this problem is that ultimately, by taking R cross F of each of these components, that's essentially what's going on. See, what this gentleman in the back is saying is, aren't we doing just a weighted average? Yes. What the cross product is doing is figuring out how much of each of these vectors is contributing moments about the x, y, and z axes. So, to use your analogy, once you've done the cross products, if you want to use that component to do, or that process to do a weighted average, that's fine. That's what the cross product is revealing for you, is how much of those components are generating moment about the x, y, and z axes respectively. But the idea is that the process is completely the same. We have the r vectors defined for each force. We have the f vectors defined for each force. So for example, if I wanted to determine the resultant vector, all I would do is add these up. 300 plus 707 plus 600 is, I don't know, 1607, something like that. The y component, negative 600, 0, and 1039, I think that's 439. And then the k component, 200 minus that plus 0 is negative 507. So if we wanted to determine the resultant vector, so summing forces and moments, the resultant vector is just going to be FB plus FC plus FD, which is 1607I plus 439J, yep, minus 507K. And this is in newtons. Now, to go to your analogy, what we're going to have to do is we're going to have to take the cross product of each of these respective pairs to determine how much moment we're going to use in this weighted average analogy when we sum these up. So if we do this first one, I'll walk you through the first one. So the first one, we're going to take the cross product of the first vector with the second, sorry, whoop, and chug this out. Now, there's also another point I kind of wanted to make about this problem, and this is really just sort of a point of personal preference. You don't have to do this, but if you notice at the very top of the problem, let me scroll up a little bit, the dimensions for this problem were given in millimeters, and if you notice, each of these are in meters. So the vectors, the position vectors, look a lot smaller than they would if you were to just write them out. I kind of think it's worthwhile to take the numbers and maybe try and make them a bit more manageable. There is a reason why, for example, in civil engineering, there is a reason why we express things in kips instead of pounds, because the numbers get so, stupid large that after a while, how much does that column hold? Well, it holds 9,487,252 pounds. Just convert it to kips to make the numbers a bit more manageable. So what I did is I took the millimeters and converted them to meters so that my moments at the end of the day would be a little bit more manageable. So if these are in meters and these are in newtons, whenever I do a cross product, I'm going to get newton meters. Your homework problem has a similar connotation, and so you don't have to do that unit conversion, but you can if you want. I kind of recommend it just because I think the numbers get a bit more manageable. So for this first one, all we're going to do is we're going to cross I, J, and K with, cross R with F. So we write I, J, K, we write 0, 0.75, 0, 0.05, 300, negative 600, 200. And so I'm not going to, chug this out. I think at this point you all can probably do that on your own. And when you chug this out, you end up getting 30I plus 0J minus 45K. And this is in Newton meters. Again, if you leave these in millimeters, this will be like 30,000. This will be 45,000. I just think it makes the math a bit cumbersome as you go through the calculations. That's just me. It's not necessary, but that's just sort of, what I think. When you do the rest of them, I'm just going to give you those answers because I kind of think you probably should have something to go off of. I think you need to get some practice in terms of computing cross products. This one ends up being 0i plus 17.68j plus 0k. I'm writing it in this, I'm writing the zeros out because the idea is that you can stack the vectors on top of one another, add the I components, add the j components, add the k components. It may seem like a little bit of extra writing, but I have found it reduces error. And so the last one, when you chug this out, you get 0i plus 0j plus, it's like 163.9k. And so all you have to do is add up this, that, and therefore your resultant moment is the sum of R cross F. And so we've got our resultant vector from before. Bless you. 1607I plus 439J minus 507K. And then M is, what do we get? Let me write that down here. Hold on. We get 30I plus 17.68J plus 118.9K. The idea on this problem is that I'm really not interested in chugging this out with you together. The idea is that as you're studying and doing your homework, that this is another set of data that you can use to validate your calculations. And ultimately, if we were trying to find a location to place this resultant to generate the same amount of moment, and we went through the cross product again, solved for Rx, Ry, and Rz, that Rx and Ry and Rz would be sort of a weighted average, okay? There is a more elegant way of doing that later, which is the resultant. However, we kind of also need this approach for what we're about to do next, which is support reactions, okay? There is a method to the madness. Trust me. That's all I got. I will see you all on Friday. We start doing equilibrium.